Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the phase diagram of pure substance. A substance that has a fixed chemical composition throughout is called a pure substance. Water, nitrogen, helium, and carbon dioxide, for example, are all pure substances. The state of a simple compressible substance is fixed by any two independent intensive properties. Once the two approximate properties are fixed, all the other properties become dependent properties. Remembering that any equation with two independent variables in the form z equals z x y represents a surface in space. We can represent the PVT behavior of a substance as a surface in space, as shown in Figure 5.1. Here, T and V may be viewed as independent variables, and P as dependent variables. Two PVT surfaces are shown here. One is for a substance that contracts unfrozen, and the other is for a substance that expands unfrozen. All the points on the surface represent equilibrium states. All states along the path of a quasi-equilibrium process lie on the PVT surface, since such a process must pass through equilibrium states. The single-phase regions appear as curved surfaces on the PVT surface, and the two-phase regions as surfaces perpendicular to the PT plane. This is expected since the projections of two-phase regions on the PT plane are lines. All the two-dimensional diagrams we have discussed so far are merely projections of this three-dimensional surface onto the appropriate planes. A PV diagram is just a projection of the PVT surface on the PV plane, and a TV diagram is nothing more than the bird's eye view of this surface. The PVT surfaces present a great deal of information at once. But in a thermodynamic analysis, it's more convenient to work with two-dimensional diagrams, such as the PV and TV diagrams. The PT diagram of a pure substance is often called the phase diagram, since all three phases are separated from each other by three lines. The sublimation line separates the solid and vapor regions. The vaporization line separates the liquid and vapor regions, and the melting line separates the solid and liquid regions. These three lines meet at the triple point where all three phases coexist in equilibrium. The vaporization line ends at the critical point because no distinction can be made between liquid and vapor phases above the critical point. Substances that expand and contract unfrozen differ only in the melting line on the PT diagram. There are two ways a substance can pass from the solid to the vapor phase. Either it melts first into a liquid and subsequently evaporates, or it evaporates directly without melting first. The latter occurs at pressures below the triple point value, since the pure substance cannot exist in the liquid phase at those pressures. Passing from the solid phase directly into the vapor phase is called sublimation for substances that have a triple point pressure above the atmospheric pressure, such as solid carbon dioxide. Sublimation is the only way to change from the solid to the vapor phase and atmospheric conditions. Have a look at the diagrams include the solid phase as well as the solid liquid and the solid vapor saturation regions. The basic principles discussed in conjunction with the liquid vapor phase change process apply equally to the solid liquid and solid vapor phase change process. Most substances contract during a solidification process. Others, like water, expand as they freeze. The PV diagrams for both groups of substances are given in figures. These two diagrams differ only in the solid-liquid saturation region. The TV diagrams look very much like the PV diagrams, especially for substances that contract unfrozen. We are all familiar with two phases being in equilibrium, but under some conditions, all three phases of a pure substance coexist in equilibrium. On PV or TV diagrams, these triple phase states form a line called the triple line. The states on the triple line of a substance have the same pressure and temperature, but different specific volumes. The triple lines appears at a point on the PT diagrams and therefore is often called the triple point. For water, the triple point temperature and pressure are 0.01 degrees centigrade and 0.6117 kilopascal, respectively. That is, all three phases of water coexist in equilibrium only if the temperature and pressure have precisely these values. No substance can exist in the liquid phase in stable equilibrium and pressures below the triple point pressure. The same can be said for temperature for substances that contract unfrozen. However, substances at high temperatures can exist in liquid phase and temperatures below the triple point temperature. For example, water cannot exist in liquid form in equilibrium and atmospheric pressure and temperatures below 0 degrees centigrade, but it can exist as a liquid and minus 20 degrees centigrade and 200 megapascal pressure. Also, ice exists at 7 different solid phases and pressures above 100 megapascal. Okay, that's all for this task. Thank you very much and see you next time.